Okay, so let's say that we have a curve like the one that's on the notes right now, and we need to figure out the integral. The integral, remember, is the area under the curve that is enclosed between the curve and the x-axis. So kind of like what we did in class, if we need to find the area, since this is an irregular shape, we need to use either the RAM or the LRAM or the midpoint formula, or midpoint formula, so that we can figure out the area by approximating it with many rectangles. So let's say that I draw rectangles for this curve. So I have these rectangles, and let's say that I draw many of them. So I can slice it as thin as I can possibly get it to be, so that there is nearly no, I guess the length of the base is very small. So you can see that as I decrease the amount of gap or the base, the length of the base, then I can actually get as many rectangles as possible, which will make my area more accurate. So let's kind of do that. So remember that rectangle, the area of a rectangle is base times height. So the height of every one of these triangle is the y value. So let's say my first one, the first height is f of x1, x1 being the first rectangle, and then my base is going to be delta x, which means the width of the rectangle. My second rectangle is f of x2, the height of x2, and since it has the same base, it's also delta x. And then I would add my third area, which is f of x3, that's the height, times the base. And then I will keep going until I add up all of my rectangle area together. So when we're actually talking about this rectangle plus that rectangle and that rectangle, and then we're adding all of them up, and since they're all very similar, they have the same width for the base and just different height, we can actually write this in summation notation. So it is the sum of all the area of the rectangles where the height is always x, f of x I times the base, where I starts at 1 and then it goes to n being however many rectangles you have. Okay, so just to make this clear, this is the height of the rectangle, and then this is the base of the rectangle. Now let's say that we don't have a very curvy graph. We have something that is actually something we can actually calculate the area of. So for example, this is called a definite integral. So let f be a function defined on a and b, the interval a and b, and let the Riemann sum, the sum of f of xi times delta x from I equals to 1 to n, so this is called a Riemann sum, be defined according to the Riemann sum. The definite integral of f over ab is given by, okay, so this is great that we wrote this in Riemann sum, but we're going to write this in integral notation. Integral notation looks like this really long S-looking thing. This is called the integral. The integral of f of x dx from a to b. Okay? A is where you're starting from on the interval, and b is where you end up. F of x, remember, is still the height, and dx just means delta x, so that's the base. So we're going to add up everything, and then this integral notation kind of replaces the summation notation. So that is the same as saying the Riemann sum, which is the sum of f of xi delta x from I equals to 1 to n, and then we're going to make n go to infinity, meaning we are trying to make as many rectangles as possible. Okay, and then provided that the limit exists, if the limit exists, then we say that f is integrable on interval a and b. Okay, so let's look at this question of definite integral. Definite integral means that we can actually find the area because the curve itself is something that we can work with. Okay, so for example, this one, find the integral of 2x from 1 to 5. Okay, so what you're going to do is this 2x is the function, and we need to find the area of this function underneath the function from 1 to 5. So the first thing you want to do is just graph that function. So you're going to start graphing this function. The slope is 2 over 1. Okay, and then you just draw a straight line through. So this is my function. And we're trying to find the area of under this function from 1 to 5. And remember that the area is enclosed by x-axis. So we have this curve right now, or this area right now, and it's basically a trapezoid. We know that the interval is from 1 to 5, so this part is 4, and on the side, we know that this length on the left is going to be 2. If you kind of look at the graph, you can tell. And then on the right is 10. And remember, the area of a trapezoid is 1/2 h times b1 plus b2. H means the height. The height is 4. b1 is the first base. It doesn't really matter which one you make the first base. Let's just say 2. Base 2 is 10. And when you solve this, you get 24. So the area or the curve, or the integral is 24. Now you're going to do these two practice problems, or actually 3 practice problems, and then when you're done, come back and then check the answer. So you're going to pause the video right now, come back, check the answer, and then I'll go over some parts that may be confusing. Okay, so check your answers to see if you got them all right. Okay, so some tricks on these. Let's say you really don't want to be drawing this graph out every time, which is actually something you don't want to do. What you can do is kind of look at the function. So anything that's a definite integral is going to be something that's solvable. So if you look at the function, for example, the first one, 3x plus 1, you know that is going to be a straight line. The problem is you just don't know if the area under the curve is going to be a trapezoid or a triangle. You can kind of visualize it and then determine whether it's going to be a trapezoid or a triangle, so you can use the right formula. Or you can graph it out if you want. But once you figure out what kind of shape it is, so for example, this one is going to be a trapezoid, then what you can do is just look at the height. The height is always going to be the distance between the interval, which is the highest number, which is 4, minus 2, which is 2. Okay, so that's easy to find. The first base is going to be how high the value is for that function at the first the start of the interval. The start of the interval is at 2. So what you're going to do is just drop in that 2 into the function, and then you get a 7. So you know the first base is going to be 7. The second base, same idea, except this time you're going to use 4, which is 13. And now you have everything you need to solve this problem without drawing out the area. Number 2 is even easier. You have a constant line at 5, so this is always going to be a rectangle. You just need to figure out. So 5 is going to be the height, it's constant. You just have to figure out how long the base is, which is going to be 3 minus 2, which is 1. Okay, number 3 is the same thing. Negative 3x plus 2 is still a line. Again, you just want to figure out if it's a trapezoid or a base. And this one is a trapezoid, so you use the same logic as number 1.